Hello everyone. In our last video, we explored 8 distinct algorithms that were aimed at improving the efficiency of the attention mechanism by minimizing its memory and arithmetic complexity. In this video, we'll be presenting a PyTorch implementation of 4 of those algorithms that have linear complexity with respect to the sequence length. This demonstration is intended to help you get familiar with the underlying concepts. So we'll be working with this Jupyter notebook and we'll use PyTorch to build those different attention algorithms. So at first we will import these 2 modules that are required for this hands-on exercise. And at first let's also look at the theory. So we assume that we are given input x, which has dimensionality n by d, so that is our input tensor. And we also have this projection matrices WQ, WK, and WV. And for simplicity, we assume that the dimensionalities of these DQ, DK, DV are all equal to D, which is the input X representation. Once we have these 4 matrices, then we can build our Q, K, and V query, key, and value with these projections. So Q, K, and V are obtained with projection of X with this WQ, WK, and WV. So let's define our parameters. So since we want to work with long sequences, we assume that n, which is the sequence length, is 1000, and the dimensionality of the representation vectors is 256. And as I said, for simplicity, DQ, DK, and DV are also equal. So now let's build our input X. So X is equal to torch.rand, and the dimensionality is n by d. And I have put some printf statements already in this notebook so that we can see the dimensionality of these different tensors. So after X, we then build WQ, also using random, so torch.rand, and the dimensionality is d by dq. So we do the same thing for WK and WV. And then we print their shapes. So X is 1000 by D, or 1000 by 256, so that is n by D, and these are D by dk, D by dq, dk, and dv. So now we are ready to build our query, key, and values. So Q is X, so that is dot product between X and WQ, so we use matmul, x.matmul with WQ. And similarly for K, we say x.matmul WK. And for V, we say x.matmul WV. Yes, so Q, K, and V are also n by D. Now, let's go over the original scale dot product attention, which has quadratic complexity. And we can use this equation, which is the softmax of QK transpose, the dot product between Q and K, and then we scale that by a square root of dk, and then we multiply the entire product with V. So we do that in these 3 steps. Step 1, we compute the attention scores. So for attention scores, that is defined as QK transpose. So we say Q dot matmul K transpose. For transpose, we use this dot T. So that gives us the attention scores. And in step 2, we need to do normalization using softmax. So normalization and scaling. So we do those 2 here. So we call them attention weights equals, so that is attention scores. So we use torch.softmax before that. attention scores, then we scale that using math.sqrt of dk. And we also need to specify the dimensionality, like we want to apply softmax over the rows, right? So we say dim equals 1. So we can say dim equals 1. We have to be careful with the dimensionalities. So in this case, our queries, keys, and values, they are all two-dimensional, so we don't have any batch dimension. So 1 is fine. But if we had the batch dimension, then we should have used 2. Or if we use -1, that is safer, because -1 would work for both cases. And we do have a sanity checking, just for since we know that softmax, like the output of softmax, will all sum to 1. So let's do that real quick. So we say sum over rows So we use torch.sum to calculate the sum over the rows of attention weights. And we say dim equals, the same thing as before, we want to do that over the rows, so we say -1. So we build the sum over the rows tensor here, and then we compare that with torch.onceLike that is built here. And we expect the result to be true, the result of torch.allClose. And then in step 3, we compute attention output. So all we need to do now is to multiply these attention weights with V. So we say attention weights dot matmul with V, and that will give us the final output. So let's run this cell. So okay, I have some over the rows, but here some off rows, so some over rows. So let's run that again. So as you can see, attention scores is n by n. Attention weights is also n by n. The sanity check is true, and the final output is also n by d. So the fact that attention scores is n by n, that is the QK transpose. So this will make it, both in terms of memory and arithmetic complexity, to be quadratic. So in the rest of this video, we will see other algorithms that will reduce this complexity. But before we do that, we also should note that when we are dealing with deep learning frameworks, we always have a batch dimension. But in this exercise, we didn't have any batch dimension. So let's, for practice, let's also build the batch version of these query keys and values. So to do that, we use q.onSqueeze, and we add one dimension from the left. So that is batch q. We also build batch k. And batch v. Alright, so now we have the batch versions of query, key, and value. And now to compute the attention scores, that is that QK transpose. So now we cannot use the matmul, we should use torch.bmm, that is the batched matrix multiplication, and we provide the two matrices that are involved in this dot product as arguments. So the first one is batch q, and the second one is batch k, but k must be transposed. And here is another thing, so we cannot use .t here, we should use .transpose, because batch k has 3 dimensions. So which dimensions we want to transpose? That is dimension 1 and dimension 2. So that gives us the attention scores. And then we do normalization, so attention weights, that is torch.softmax of attention scores. divided by math.square root of dk. And we specify the dimensionality, which dimension we want to compute the softmax. So we want to do that over the rows, and here we can use either true or we can use -1. So -1 means the last dimension. And for sanity checking, we still do that. So sum over rows equals torch.sum of these attention weights, and dim equals same as here, -1, and this one should be sum over rows. And now in step 3 we can compute the attention output. So that is attention weights dot matmul with, oh, here is what I'm doing wrong. So since we have batch versions, we should use torch.bmm of attention weights, comma, batch v, and that will do it for the batch versions. So now you can see batch q is 1. The first dimension is 1, but that is the batch dimension. So b, n, and d. Attention scores is b, n, n, and attention weight is also the same. So the error that I'm getting here, yeah, it looks like I have another sum of rows. So sum over the rows, and then we can see the attention output is also b, n, d. So now let's move to the first method that reduces the complexity, and it is called efficient attention. So we use this equation. The key idea here is that instead of computing qk transpose, they first compute this sigma call of k transpose times v. So by changing the order of computations, they reduce the both memory and computational complexity. And the sigma here stands for softmax. When it's sigma row, it means it is applied to rows, and when it's sigma col, means it is applied to the columns. So for the rest of this video, we will be using just the normal q, k, and v, not the batched versions. All right. So now we do this in these 3 steps. First, we apply sigma to q and k. So we call them sigma q is torch.softmax of q, and we specify dim equals 1. So q is has 2 dimensions, and we want to apply that to the rows, so that is 1. And sigma k is torch.softmax of k, and we apply that to the columns. So for that, we specify dim equals 0. So that is it for step 1. Now in step 2, we want to do this computation in this parentheses. So we call the result of this step 2 result, and we do this sigma k, and here we have to transpose this sigma k. So we use that t, and then we do matmul with v. Matmul with v. And then in step 3, we calculate the final output. So that is attention output equals this multiplication, sigma row of q times this step 2 result. So that is sigma q dot matmul with step 2 results. So let's run this cell, and we can see sigma q, sigma k have the same dimensionality as q and k, but the step 2 result is d by d, which is much smaller than n by n, assuming that n is large. So this way, by switching the order, instead of computing q times k transpose, they did k transpose times v, and this way they were able to reduce both memory and arithmetic complexity. So method 2 is also very similar. So instead of using sigma for sigma that is applied to q and k, they define this feature function phi, and this is like a kernelized version of attention. And when you do this, then you can change the order from, instead of computing phi of q times phi of k transpose, you can compute this quantity first, that is phi of k transpose times v, and then you bring in the phi of q from the left. And what feature function? They use this feature function ELU of x, which is exponential linear unit. The curve for ELU of x alone is this blue curve, but as you can see, it is negative when x is less than 0. So since for kernel attention, for any kernel function, we should not have any negative feature function. Then they added this +1. So by this +1, it shifts the curve toward positive regions. So let's build our feature function x, feature function phi. So that is, at first we build ELU using torch.nn.elu, and then we build our phi feature function as ELU of x +1. So now we do this in these 3 steps. At first we apply phi to q and k. So we say phi of q equals phi of q, phi underscore k equals phi of k. And then we move to step 2, we compute the step 2 result. That is, the step 2 result equals, so for step 2, this is our step 2, phi of k transpose times v. So we say phi underscore k dot t for transpose, and then .matmul with v. And the final output is phi of q dot matmul with step 2 result. Right. So this was very similar, except that instead of using the sigma in method 1, they used this feature function phi. So now moving to the third method. This method is using first order Taylor series approximation. And the final equation is given here. So 1 sub n stands for a vector of all ones, and q prime and k prime are the normalized version of q and k. And this normalization is based on the L2 norm. So as a prerequisite, first we need to build this 1 sub n. So we do that by torch.ones. And this will build this vector which has 1000 ones in it. Now we do this also in these 3 steps. So in step 1, we normalize q and k. So that is this q prime and k prime. So first we compute norm of q. That is the L2 norm of q. So we use torch.norm applied to q. And for L2 we use p equals 2. And we use dim equals 1. And we maintain the dimensionality using keep dim equals 2. We do the same thing for k. Norm of k equals also torch.norm k, p equals 2, dim 1, and keep dim also true. So after we build this norm of q and norm of k, then we compute q prime as q divided by norm of q, and k prime is k divided by norm of k. So that is it for step 1. In step 2, now we build or we compute these 3 terms. So if you look at this equation, we have 4 terms, 2 in the numerator and 2 in the denominator. But this one is just a constant, that is the sequence length. It's not constant, but because the sequence length could vary. But we have that as n, right? So we define n as a scalar value. So we have term 1, v transpose dot 1 sub n, and then term 2 is this, term 3 is this one. So term 1 is v transpose, so we say v dot t dot matmul with 1 sub n. So that is for this term. Then term 2 is q prime k prime transpose v. So at first we build or we compute the quantity inside this parentheses. So term 2 is so that is k prime dot transpose dot t, then dot matmul with v. And now we bring q prime from the left. So we say, let's put this into parentheses, and then we say q prime dot matmul this. And finally term 3. Term 3 is also very similar to term 2, except that, so we can copy that. And instead of v, we use 1 sub n. And then finally, the attention output is term 1 plus term 2 divided by n, which is a scalar value, plus term 3. But there is a problem here. The dimensionalities of the numerator and denominator do not match, so we will get an error. So, but we'll fix that later. So norm of q is n by 1. So that it still has 2 dimensions because we used keep dim equals true. Otherwise, it would have been just n. Term 1 is a vector of size d. Term 2 is n by d. Term 3 is n, a vector of size n. But this division did not succeed because of this dimensionality mismatch. So all we have to do, we just need to add one dimension from the right side of this term 3. So we can say unsqueeze -1. And let's run that again, and yes, that works. So as you can see, this was another method for linear complexity of attention. And yeah, now moving to method 4. This method is called Linformer's attention, and it is using a low rank approximation. And they bring in 2 new random projection matrices E and F, which has size R by N. And R is the assumed rank of the attention matrix. So once we compute, build this E and F, then we compute these projection matrices EK and FV, which have dimensionality R by DK and R by DV. After that, we build this context mapping matrix P, as shown here. So this is similar to the original attention equation, a scale dot product attention, except that instead of K, they are using EK. And finally, the final output is P times FV. So for the prerequisite of this, we assume that R is 100. And because we assume that sequence length is 1000, so R must be something much smaller than 1000. So we say 100 is a good assumption. So then we build this E and F. So E is torch.rand, and the dimensionality is R by N. So R is defined here, and we say torch.rand Rn, and F is torch.rand also Rn, And now we do this into these 3 steps. In step 1, we compute EK, that is E dot matmul with K, and FV is F dot matmul with V. Then in step 2, we compute this context mapping matrix P, so that is torch.softmax of q.matmul with ek.t, and then we divide that by a square root of dk, and we run that over the rows, so that is dim equals 1. And finally, the attention output is p dot matmul with fv. So now notice that ek and fv have dimensionality r by d. So it is reducing the dimensionality of k and v from 1000 by 256 to 100 to 256. And then the context mapping matrix P is n by r, so 1000 by 100. So previously in the original scale dot product attention, this was 1000 by 1000. So this is how they reduced the complexity. So that brings us to the end of this video, which is the first hands-on video in PyML Studio channel. I hope that the detailed walkthrough of the implementation has helped clarify the concepts. You can find the links to this notebook and its solution in the description. Thanks for watching and happy learning.